choose the good force sensor. So for the different cases here, for the 4 diameter, so we can see that the maximum force will be reached in dense sand, of course, and we have different values here. And so in the maximum expected load based on the CPT is for the biggest diameter, and we are over 1,500 decanewtons. So we have to choose the sensor a little bit higher. So the one of 2,500 decanewtons. Okay. Is it clear? No? It's not complex, but if it's not clear, I can explain. All right, so we can start the experiments now.
Because usually we have Germany, so we don't keep the kind of because like tons.
Good. Yes. So it depends on the people, and decanewtons is linked to kilograms. Okay, it's similar. All right, and that's why I use this here, but I make the calculations in kilonewtons just to make confusions in your spirit. Yeah? Okay, but it's always the same thing. Yeah? It's newtons. Okay, and so the question that follows is about buckling. Is there a risk of buckling when we jack the pile? So in your case, I didn't say all the things, but we assume that there is a ball joint at the top of the pile. And for buckling, we will use the worst formula of Euler, so this one. And so we can calculate, we know all the parameters. We know E, the Young modulus, I, the inertia, and L, the length. So we can calculate the force and evaluate if there is a risk of buckling during the test. Because if the pile will buckle, well, we cannot perform the experiment. So we have to estimate. This is an estimation also. Huh? So I've done the calculation here for the different diameter of piles. And so we can see that the buckling force here varies so with the diameter, of course. And we are we can compare those values with the values obtained for the maximum load necessary to install the full pile at the depth that we want. So if we compare here, well, we need 7,500 newtons, and the buckling factor is at 4,369. So we will have here a risk of buckling. In this case, the second case, the value are a little closer, but there is also a risk of buckling. And for the third case, again, sorry. And for only for the last, in the last configuration, we will have no risk here of buckling. So it is important to have this value in mind, but in practice, it's more complex because the buckling, the force of buckling I calculated here was, the calculation was done by assuming that the whole pile was outside the soil. But in practice, we need a small force for installing a little bit the pile, and so the length outside the soil will be reduced. Reduced during the installation. So we have here an estimation of the risk of buckling in your experiment. Okay, so we have to have that in mind, but we took the risk, in fact, and we gone to perform the test. So the different tests here that we performed, so I put the results for both the dense sand on the left and the medium dense sand on the right. So you had one more case with a smaller diameter of pile, and so you can see here the results. So those data are available on the data paper, so you can download it and modify, work on those data here. Okay. So is it clear for the buckling? I think. Okay, and so the question after the fifth one is relative to the data which is in the data paper, and so the question is about the influence of the pile diameter on the result, on the compressive load, compressive resistance, and also on the tension resistance for the sixth question. So we have two configurations, dry sand and saturated sand. Okay. Oh. So we have 10 minutes left. I will let you to do this time before. Is it okay? Yeah? No. Completely. So you have a PDF that describes the test. Yeah. Okay. We are in now, so this is the exercise, but here it's a PDF file that describes this one, yeah? And you have the different files. The data paper is a way also to publish results that are not interpreted. And we have a DOI number, so it's identified documents that can be shared or not. To be on the depository. What happens? You decide for that
Also schon alt, hatte ich.
Ja, ja. Nee, ja, das ist so gut. Ja, das ist okay, was er war.
Okay.
So abgeben ist auch so, glaube ich, recht gut. Das Ding steht da. Was ist
dass es significant besser so alles ausgedrückt bekommt. Was im Excel drin? Was hat uns geschickt?
Nee, das ist der Sache. Okay, aber das heißt ja, wir müssen ganz runter, ne? Das ist fertig. Maximal. Oder? Check.
Okay, so the treatment may be more or less long. Some of you have opened softwares to interpret the data. Anyway, this type of file data paper is very useful for your scientific work. If you are experimentalist, you can publish data more or less raw without interpretation, and other people can use it if you agree later on. But you are the owner of the data anyway. Okay, so the question was about the maximum resistance. So I come back to this file. I send you also this PowerPoint, so you can work on it if you want later. There is no difficulty. So we can see here on the compression resistance that for dense sand, depending of the diameter, we have of course an evolution of the resistance with the diameter, and it is quite different if the sand is dry on the left or saturated on the right. Okay, and so this is due to soil mechanic concept. We work with effective stress, so the resistance is also linked to the effective stress, and which is higher in saturated soil. There is a difference also, so you can imagine that in between dense and medium dense sand. So it's the other data paper mentioned at the end of the exercise. And we may have a factor of about 3 in between the two behavior. So it's very important to have an idea of the soil properties in order to evaluate the resistance of deep foundation. Okay, for the principle, so you can work on the data and you will have those results depending on the type of piles. We have also a small difference in between the case of open piles and closed piles. So the open pile have a resistance a little bit lower than the closed pile, but this difference varies a little bit with the diameter. And so in some cases, we may have a plugging effect. So particularly in dense sand, the sand makes a plug at the bottom of the tip of the pile, and this change the behavior. It comes from friction pile towards a pile with a end-bearing capacity added in the behavior. So in this case, we cannot share and discuss so much, but it may be it may have an effect also. And concerning tension, so in the second phase of each test, so after jacking, we came back to 0 force, and then we make a upload loading vertical to the top, and you can see here the effect of the diameter on the sand, open or closed, then sand in saturated medium or in dry sand. So if the sand is dry, we have higher resistance, also depending on the diameter. Okay, so that's what I wanted to show you this afternoon. I hope you had some interest. Do you have any question? No. Yes. Yeah.
You mentioned the plugging effect. Any studies, like theoretic studies in symmetry of the occurring of plugging of that?
I don't know precisely, but I can say that we had plugging in small diameters of files, so we observed that, but it was not really a study. And what we also observed is that in the plug, the sand has been crushed a little bit, so the granulometry, the grain distribution is finer than originally. So we have this phenomenon, which is also quite important for Fontainebleau sand. If we are going over 1 to 5 megapascal of stress, we may have crushing. So this is an artifact because if we simulate not a small pile like that, but a pile 100 times bigger, they will not have plugging in this sand because there is no hatching and so on. Okay. Thank you for the question. Other questions? No? Okay. So I give the floor to Professor Zackert from. Let's go.